Imagine living in a world where up, down, left, right, forward, and backward aren't the only directions you can move in. Welcome to the concept of extra dimensions. Our everyday lives are dominated by three dimensions of space: length, width, and height, and one of time. This four-dimensional framework is so ingrained in us that anything beyond it seems unthinkable. Yet some theories propose the existence of extra dimensions, dimensions beyond the ones we can perceive. These aren't just abstract mathematical constructs, but could be as real as the dimensions we're familiar with. They might be hidden, curled up in spaces too small for us to notice, or they might be macroscopic, extending infinitely, but in a direction we can't point to. So let's delve deeper into this mind-bending concept and explore what it could mean. Before we leap into the unknown, we need to understand what we already know, the three spatial dimensions and one time dimension. Let's begin with the basics. We live in a world of three dimensions: length, width, and height. These dimensions form the framework of our reality, allowing us to move forwards and backwards, side to side and up and down. Imagine a line. It has only one dimension, length. If we add a second dimension to that line, we get a square. Now we have length and width. Add a third dimension and we have a cube, which adds height to our two-dimensional square. These three spatial dimensions construct our physical world, but we also live in time, don't we? Time is often considered the fourth dimension. It's a bit different from our spatial dimensions, though. We can move freely in space, but we're all passengers on the time train, moving in one direction, forward. We remember the past, we live in the present, and we anticipate the future. Time gives our existence a sense of continuity and direction. So, we've got our three spatial dimensions and one time dimension. But what if I told you there might be more? That's where things get interesting. Scientists, particularly those delving into string theory, suggest that there could be additional dimensions, dimensions beyond our perception. These are not just theoretical musings. There are serious scientific propositions backed by mathematical models suggesting that our universe may have more than the four dimensions we're familiar with. These extra dimensions could be tiny, curled up so small that we can't detect them. Or they could be as large as the dimensions we know, but somehow invisible to us. We call these macroscopic extra dimensions, and exploring these extra dimensions could be the key to answering some of the most profound questions about our universe. Now that we have a grasp on our familiar dimensions, we can venture into the realm of the extra dimensions. So buckle up. We're about to journey into a world that challenges our intuition and stretches our imagination. Enter string theory, a theoretical framework that not only proposes but requires extra dimensions. Now, this might sound like a tongue twister, but let's break it down. String theory is a theoretical framework where the point-like particles of particle physics are replaced by one-dimensional objects called strings. In the world of physics, there are four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. For a long time, scientists have been trying to find a unified theory, one that could explain all these forces in the same language. And here's where string theory comes into play. String theory suggests that everything in the universe, from the tiniest particle to the most gargantuan galaxy, is made up of tiny, vibrating strings of energy. But for this to work, we need more than our familiar three dimensions of space and one of time. String theory says we need 10, or in some versions even 11 dimensions. Now you might be wondering, where are all these extra dimensions hiding? Well, string theory suggests that these extra dimensions are compactified or hidden because they're incredibly tiny. So tiny, in fact, that they're almost impossible to detect. But here's the twist. While some theories propose that these extra dimensions are minuscule, others suggest that they could be large or macroscopic. And it's these theories that propose the existence of macroscopic extra dimensions that we're especially interested in. These theories suggest that we live on a three-dimensional brain or membrane which is embedded in a higher dimensional space. And it's in this higher dimensional space that gravity could exist, potentially explaining why gravity is so much weaker than the other fundamental forces. And it's within this theory that we find the concept of macroscopic extra dimensions. So as we delve deeper into the mind-bending world of string theory and extra dimensions, we continue our quest for a unified theory, one that could potentially revolutionize our understanding of the universe. Unlike the tiny, curled-up extra dimensions of string theory, macroscopic dimensions are, well, larger, much larger. To grasp this, let's first consider that we live our lives in a world of three spatial dimensions: up, down, left, right, and forward, backward. And then there's that elusive fourth dimension, time, that ceaselessly moves us from the past, through the present, and into the future. But what if there are more dimensions out there, dimensions that are not microscopic and curled up, but macroscopic and large, just like the three spatial dimensions we know and love? This is where the concept of macroscopic extra dimensions comes into play. In contrast to the more familiar dimensions, these macroscopic extra dimensions would be significantly larger, possibly even infinite. They wouldn't be bound by the confines of the tiny, curled-up dimensions of string theory. Instead, they could extend outwards forever, beyond our three-dimensional universe. But here's where things get really interesting. If these macroscopic dimensions exist, they could be hiding in plain sight, so to speak. We wouldn't necessarily be able to see or touch them, as our senses are geared towards our three-dimensional reality. But they could still have a profound impact on our universe, influencing the behavior of gravity and other fundamental forces. The concept of macroscopic extra dimensions isn't just a fanciful idea, it's an active area of research in theoretical physics. Scientists are working on ways to detect these dimensions using everything from particle colliders to precision measurements of gravity. So the next time you're looking up at the night sky, consider this. Beyond the stars, galaxies, and vast cosmic structures, there could be entirely new dimensions waiting to be discovered. Dimensions that are immense, unseen, and full of potential. It's a thought that's as humbling as it is exciting. And if these dimensions exist, they could have some pretty mind-boggling implications. So what would it mean if these macroscopic extra dimensions were real? What could we see or measure or test? Well, let's dive into the realm of observable effects and experimental implications. If macroscopic extra dimensions are indeed a reality, they could have profound effects on our understanding of gravity and particle physics. To start with, gravity could behave differently. In our three-dimensional world, the force of gravity decreases with the square of the distance between two objects. But if additional dimensions exist, gravity might not fall off at the same rate. It could be weaker or stronger, leading to deviations from Newton's laws that we could potentially measure. Next, let's consider particle physics. The existence of extra dimensions could significantly impact the properties of fundamental particles. For example, if particles can move in these extra dimensions, they might have different energy levels than predicted by standard models. This could potentially lead to new, unforeseen particles or discrepancies in particle behavior. Moreover, the presence of extra dimensions might also influence the propagation of light and other electromagnetic waves. This could result in observable effects, such as changes in the speed of light or alterations in the behavior of electromagnetic fields. But how do we test these possibilities? Scientists are devising ingenious experiments to search for signs of extra dimensions. For instance, they're looking for tiny deviations in the behavior of gravity or particle interactions that might hint at the influence of additional dimensions. They're also studying cosmic phenomena, such as black holes and cosmic rays, for any signs of unusual behavior that might point to the existence of extra dimensions. In essence, the presence of macroscopic extra dimensions could fundamentally alter our understanding of the universe. It would open up new avenues of exploration and challenge our long-held assumptions about the nature of reality. These dimensions, if they exist, could be hiding in plain sight, subtly influencing the physics we observe. But like any theory, the concept of macroscopic extra dimensions has its critics and rivals. Yes, that's right, not everyone is on board with the notion of macroscopic extra dimensions. Some critics argue that the evidence supporting their existence is circumstantial at best. They contend that the unusual behaviors and phenomena that proponents attribute to extra dimensions can be explained by other, more conventional theories. For instance, the quantum effects that some believe indicate the presence of extra dimensions could also be the result of quantum fluctuations or quantum gravity. Similarly, the gravitational anomalies that some attribute to macroscopic extra dimensions could be explained by modifications to Einstein's theory of general relativity, such as the Monde theory, which proposes changes to the laws of gravity at very small accelerations. Even within the camp that accepts the possibility of extra dimensions, there is disagreement. Some theorists propose that the extra dimensions are compactified or curled up at incredibly small scales, rather than being macroscopic. Others suggest that the dimensions are warped, with gravity being stronger in some dimensions than others. And then there are the alternative theories. One such contender is loop quantum gravity, which proposes that space-time is not continuous but rather composed of finite loops or networks. This theory, while not explicitly requiring extra dimensions, could potentially accommodate them. Another alternative is M-theory, a superstring theory that proposes a total of 11 dimensions, 10 spatial and 1 temporal. In this theory, our observable universe exists on a three-dimensional brane within a higher dimensional space. Despite these challenges and alternatives, the concept of macroscopic extra dimensions continues to be a vibrant area of research. It's a testament to the spirit of scientific inquiry that physicists are willing to explore such outlandish possibilities. After all, these inquiries could lead to a deeper understanding of our universe and perhaps even to new technologies or insights. Whether these dimensions exist or not, exploring the concept pushes the boundaries of our understanding of the universe. As we continue to probe the depths of the universe, the question remains, will we ever find concrete evidence of these extra dimensions? This question takes us into our next discussion, the future of extra dimensions. In the world of theoretical physics, there's a hive of activity. Scientists are eagerly devising new experiments and refining existing ones, all in the hope of catching a glimpse of these elusive dimensions. The Large Hadron Collider, for instance, is being fine-tuned to potentially detect the effects of extra dimensions on particle behavior. If successful, this could provide the first tangible evidence of their existence. But it's not just about detection. Theoretical physicists are also working tirelessly to refine and expand upon our understanding of extra dimensions. They're developing new models, testing hypotheses, and challenging assumptions. This work is crucial in helping us understand how these dimensions might interact with our observable universe. The implications of this research are profound. If extra dimensions do exist, they could provide the key to unifying the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, into a single, overarching theory. This would represent a monumental leap forward in our understanding of the universe. Beyond the realm of theoretical physics, the potential applications of extra dimensions are vast and varied. In the field of technology, for example, understanding extra dimensions could lead to the development of new materials, energy sources, or even forms of transportation. It's a brave new world, limited only by the boundaries of our imagination. But let's not get ahead of ourselves. The journey to understanding extra dimensions is long and fraught with challenges, but it's a journey that we're committed to, driven by an insatiable curiosity to understand the universe and our place within it. The search for extra dimensions is more than just a quest for the unknown. It's a journey into the very fabric of reality itself. So as we look to the future, we do so with a sense of anticipation and excitement. Who knows what discoveries await us in the uncharted territories of extra dimensions? So we've taken a journey into the world of extra dimensions, a concept that challenges our very perception of reality. We started with the familiar, the three spatial dimensions and a single time dimension that shape our everyday experiences, a simple yet profound framework within which we exist. From there, we delved into the realm of string theory, a bold attempt to reconcile the seemingly incompatible aspects of quantum mechanics and general relativity. It's here that we encountered the concept of extra dimensions, ones far smaller than we could ever observe directly, yet potentially as real as the dimensions we know. We then expanded this concept to include macroscopic extra dimensions. These aren't tiny hidden dimensions, but ones that could be as vast as the dimensions of length, width, and height. We explored the Kaluza-Klein theory, which opened the door to the possibility of such dimensions, and brain world scenarios, which provide a framework for understanding how these dimensions could exist alongside our own. We contemplated the experimental implications of these dimensions, how they might influence gravity, particle physics, or even the very structure of the cosmos. We considered the challenges that lie in confirming their existence and the alternative theories that could either compete with or complement the idea of extra dimensions. Finally, we looked forward, speculating on the practical applications of these dimensions, from technological advancements to energy solutions. We've seen how this concept intertwines with other areas of physics and mathematics, fostering a truly interdisciplinary understanding. The idea of macroscopic extra dimensions is a fascinating one, and we've only just begun to scratch the surface. Our understanding could change dramatically as we delve deeper into this concept, and who knows what discoveries lie ahead in this field. Whether or not these dimensions exist, the exploration of such concepts pushes the boundaries of human understanding, and that in itself is a journey worth taking.